My name is Lee Provost. I'm a research hydraulic engineer. The project I've been working on is the investigation of ecological drivers of dune stability for coastal resiliency. It is looking at the ecological functions within a natural dune system and how those play a role in dune stability. So under extreme wave action, under extreme storm events, how is your coastal dune going to perform to protect inshore, inland infrastructure during extreme events? Basically with a dune, you kind of have this natural growth cycle, right? So you have what's called an embryo dune that gets some level of vegetation establishment, and then that encourages sediment trapping. And then that cycle continues. The sediment trapping encourages more vegetation growth, and that kind of continues until you reach some max elevation threshold. And so what's nice is with that cycle, you kind of have this full integration of vegetation throughout the dune. So it's kind of just layers of this biomass material. And that ends up adding a lot of stability to your dune. But the good thing about it is because it's a natural system, it's resilient. It can recover. It can, get washed away to an extent and then be replanted or reestablish itself and continue to grow. There's been a lot of research looking at the role of vegetation in dune stability. There's been a lot of laboratory experiments looking at mimic vegetation, replicate vegetation. There's been experiments looking at planted vegetation, transplanted vegetation, but nobody till this point has ever been able to take a section of a living dune from the field in situ where it's been able to go through this natural growth cycle and then bring it to a laboratory and be able to test it in a controlled environment. But one of the more important things that we really wanted to try and focus on was there's the existence of this AM fungi, a bruscular mycorrhizal fungi. And so what that does is through a nutrient exchange with the roots, it creates this web of hyphae, and that actually aggregates sand together. And so you end up with these large macro aggregates of sand that are just really big clump rock-like looking things. And so that was one of the biggest things that we really wanted to look at is that function actually being represented in what we're trying to model. And that was the whole thing about it, is it's not just a pile of sand. The roots really do add a level of resiliency and strength to it that a lot of people just don't realize. So we needed to kind of devise this really specific instrument, which, at the end of the day, it is a box, but it's a very specific box. But we needed something that could grab that sample with minimal impact to the sample, be able to seal it off, and then be able to transport it, because we had to bring it from Florida to Vicksburg, without falling apart. What we did find out was, from the experiments that we've done in the past and these experiments, a lot of the replicate dunes that we had evaluated before are a really good representation of a living dune, at least at the density, that we tested. And so that leads to a lot of other questions of, well, how can we build to that same level of resilience faster? So when we're planning for coastal dune constructions, the natural growth cycle takes a long time, but if we need that more immediate solution, well, what about integrating some types of these synthetic materials or coconut core materials, mimic roots to kind of build up that below ground biomass sooner. My hope is that this data can help better inform our coastal management strategies. So it's ultimately to help make more resilient coastlines, help our coastal planners build better beaches that can better protect our coastal infrastructure in the long run. ERDC has a lot of really unique capabilities in-house, including our physical modeling capabilities in our HISER facility. And so one of the biggest things we're interested in recently is the evaluation of these nature and nature-based features. It's really hard to understand living systems. Field work is difficult to instrument. A lot of the times you're waiting for extreme storm events, but one of the things that we can do with our facilities here is model these scenarios, living, non-living mimics, and we can take that data, use it to better inform our numerical models, and use it to build out more of these performance curves of how these nature-based solutions are actually performing so that those can be implemented in the field. At ERDC, we have a plethora of different expertise here, from geotechnical structures folks to ecologists, microbiologists, coastal engineers, hydraulic engineers, model shop, machine shop, welding shop, anything that you need to get done, we have that capability in-house. We're engineers, not ecologists, so we're always looping in the ecologists to help us, make the right decisions when it comes to how we're evaluating that. Because, we have our rules and how we evaluate things on the engineering side. They have their rules on how they evaluate things on the ecology side. So we work with them quite frequently, and they were a really big part of making sure this project was successful too. It's really great because when we're doing projects and planning projects, we know whose door to knock on and who to reach out to. And we know that even when we have these really challenging problems that nobody's ever tried to do before and people might think you're a little bit crazy, we know the right people to talk to that can help make that happen.